This is a presentation for the Blue Ribbons food case. The five names listed are the group members of our team. A quick introduction of Blue Ribbon Foods. Blue Ribbon Foods is a medium-sized company that specializes in canned and distributed fruit and vegetable products. They have 2 grades of tomatoes, grade A and grade B, and they have 3 products: whole tomatoes, tomato juice, and tomato paste. The current situation is Blue Ribbon Foods has a supply of 3 million tomatoes, that of which 20% must be grade A tomatoes and 80% must be grade B tomatoes. They have also negotiated an 18-cent per pound delivery price. The quality scale on average for grade A tomatoes is 9 and 5 for B. The quality standards that they have to have for whole tomatoes is 7.5 and 6 for tomato juice and 5 for tomato paste. Blue Ribbon Foods manager's goal is to maximize its profits for the tomatoes they sell and find the optimal combination of grade and products. Allen said that production would be limited to 960,000 pounds. This equation is an illustration of how he came up with that number. We set X equal to be the total production, and we also had that set to 7.5 grade. A worker named Hanita suggests to use the whole crop to make canned whole tomatoes. So is this a good choice? Well, in order to use the entire crop for whole canned tomatoes, the average point of 3 million pounds of supply has to be at least 7.5 average point per pound. So 600,000 times 9 plus 2,400,000 times 5 divided by the entire supply equals 5.8 points per pound. Because that is less than the 7.5 points per pound that we need, we can't use the entire crop for whole tomatoes. We were asked, how does Reynoso reach the conclusion that the company should use 2 million pounds of grade B tomatoes for paste and the rest of grade B and grade A tomatoes to produce juice? Well, according to Reynoso's calculation, the tomatoes paste marginal profit is the highest one. In order to maximize the total profit, Reynoso wanted to reach the maximum demand on tomato paste market. 80,000 times 25 equals the 2 million pounds. This is a management analysis of what is wrong with Reynoso's reasoning. Reynoso allocated the tomatoes cost based on the quality. However, this method overestimated the cost of product A and underestimated the cost of product B, which led to the overestimate on tomato paste and underestimate on the tomato whole product. We then turned to linear programming, where the objective function was to maximize profit. The coefficients represent profit per case of tomato products sold. For example, AX plus BX represents the poundage of A and B quality that goes into whole tomatoes, divided by 18 pounds per case. These are the decision variables we took into account when using Solver on Excel. You can look at them at your own convenience. We also were held to 3 constraints in our linear programming. We took into account first the quality constraints of each product. Because each product had quality control standards that must be met for each product, there was quality constraints. Also, there was demand constraints on production. Furthermore, supply was also constrained to 3 million pounds total. This is what our solver looked like after taking into account our decision variables and constraints. You can take a look at these at your own convenience.
After using Excel Solver, we were able to identify how much of each tomato grade will be used for the production of each product. We found that 350,000 pounds of grade A tomatoes would be used for whole tomato products, and 250,000 pounds of grade A tomatoes would be used for tomato juice. Furthermore, 210,000 pounds of grade B tomatoes would be used in whole tomato products, 750,000 pounds of grade B tomatoes would be used for juice, and 1,440,000 pounds of grade B tomatoes would be used in tomato paste products. We were asked to calculate how much of each product would be produced. Using our output from our Excel solver, we combined 350,000 pounds of grade A tomatoes and 210,000 pounds of grade B tomatoes into the whole tomato product, divided that by 18 pounds per case of tomatoes, and calculated that Blue Ribbon Foods would produce 31,111 cases of whole tomatoes. Using a similar method, we calculated that Blue Ribbon Foods would produce 50,000 cases of tomato juice and 57,600 cases of tomato paste. Next, we wanted to verify that Excel Solver gave us an adequate average quality per pound of whole tomato and juice. We multiplied 350,000 pounds of grade A tomatoes by 9 and 210,000 pounds of grade B tomatoes by 5, divided that by the total pounds of tomatoes in production of whole tomato products, came up with an average quality of 7.5, which was our target goal. Next, we used the same method for the juice products, but with slightly different quality standards, and came up with an average quality of 6.75 points. Next, we wanted to see how much money Blue Ribbon Foods would make by producing this combination of tomato products. We multiplied each of the number of cases by the coefficients representing profit earned per case of tomato products sold, as seen earlier in our optimization function, and found out that our total profit, or our revenue, would be $705,813.30. Our costs would be equal to 3 million pounds of tomatoes multiplied by the 18 cents delivery charge, giving us 540,000. Finally, our net profit would be equal to $165,813.30. Here is our sensitivity report as given to us by Excel Solver. You can pause the video and look at this at your own convenience. We'll be using these values for the next few questions. We were asked whether or not Blue Ribbon Foods should purchase 80,000 pounds of grade A tomatoes at 8.5 cents per pound. We determined that 8.5 cents would be within the allowable increase as given to us by our sensitivity report, and also found that the shadow price would be 26.1 cents per pound. Using this equation, we multiplied 80,000 pounds by the difference in potential increase in profits minus the cost of tomatoes purchased to give us a total of $14,080 increase in profits. So we determined that yes, Blue Ribbon Foods should buy all 80,000 pounds of tomatoes at that price. Next, we wanted to see how much Blue Ribbon Foods would be willing to pay for an advertising campaign that could increase its juice demand by 25,000 cases. From the sensitivity report, we found that the shadow price for juice demand would be 1.6 cents. We multiplied 25,000 cases by 20 pounds per case required and found that the demand would increase by 500,000 pounds of tomatoes. We multiplied this 500,000 by 1.6 cents to give us $8,000. Thus, the company should be willing to pay $8,000 or any price under that for this advertising campaign. We were then given the situation where the price of juice would increase 30 cents per case and asked whether or not this would change our optimal solution. We found that 30 cents per case divided by the 20 pounds of tomatoes required per case would give us a 1.5 cent increase per pound of tomatoes. This 1.5 cent increase is within our allowable increase from the sensitivity report, so there will be no change to our optimal solution. Finally, we were asked to determine how much Blue Ribbon Foods would be willing to pay for an additional 50,000 pounds of grade B tomatoes that would become available. We determined that the shadow price for this situation would be 22 cents. We multiplied this 50,000 pound increase in available tomatoes by 22 cent shadow price to give us $11,000. Thus, we determined that Blue Ribbon Foods will pay any price equal to or less than $11,000 for these additional tomatoes. In conclusion, through this case study, we learned that linear programming allows us to find the optimal allocation of tomatoes with a given set of constraints. Sensitivity analysis also helped us to determine how changes to these constraints could impact our optimal solution and ultimately the operations of Blue Ribbon Foods.